Hello, I'm Swapna, and today I'm going to talk about Newton's laws. Okay, so what I'll do is that I'll explain, why the planetary orbits, are elliptical. Okay, so you can derive that starting from the Newton's laws and using the inverse square law of gravitation. Okay, so I'll do that. So to get into before we get into the details, I'll just give a brief introduction of the polar coordinates, which we will be using a lot in our work today. So let me get started. Okay, so if you have a particle, an object, moving in a trajectory, you can describe its trajectory in terms of the Cartesian coordinates x, y. Each point is denoted by the two coordinates, x coordinate and y coordinate, right? Or you can describe the coordinates in terms of a radius vector, r, and the angle theta. Okay, so this is the polar representation. All right. So the radius vector it's a vector, and theta is the angle that the vector makes with respect to the x-axis. Okay. So what is usually done is you define a unit vector, along the direction of the radius vector. Okay, you call that r hat, and you define another vector theta hat, which is perpendicular to the unit vector, unit radius vector. By unit vector I mean a vector whose length is unity. It's of unit length. So you can write r hat as cosine theta I hat plus sine theta j hat. So this is theta, so you can resolve this into two components. All right. And theta hat turns out to be, if you just resolve it into two components, you'll see it's minus sine theta I hat plus cosine theta j hat. And you can kind of see that from the expression of r hat. You change theta to theta plus pi over 2, and you get minus sine theta. And this thing, theta hat, is just r hat rotated by pi over 2. So you get that expression. All right. So what we're going to do, so we'll be needing these two expressions, and we will need a couple of other things, that is, tools of vector calculus. So for example, let's actually do it here, I was thinking whether I should first start the derivation and then I will use some, vector identities, but let's actually get this out of the way. So you can take the derivative of r hat with respect to theta. So that means you basically take the derivative of the x component first with respect to theta, and you get minus sine theta, I hat, and if you take the derivative of sine theta, you get cosine theta j hat. Now you see, this is just what theta hat is, right? So dr hat d theta is theta hat. That's one of the relations. And in a similar way, you can do d theta hat d theta. You're taking the derivative of this with respect to theta, and what you'll get is you'll get minus r hat. You can just do the derivative, and you'll get this. So we will need these two identities. This and this one. So now, why do we need these things? All right, because I'm going to solve, Newton's law, all right, Newton's second law of motion, for the gravitational force. So let me just write down how that looks like first. So Newton's law is what? It's m d2r dt squared is equal to minus g small m capital M over r squared r hat. Right? This is the standard expression for Newton's law. Like mass times acceleration is the force. The gravitational force is directed toward the center, right? Wherever the source is, the sun. So the sun is the source. So the force is directed towards the sun. So that is indicated by r hat. So if this is where the sun is, then the force is directed toward the center. And you have on the left side, you have d2r dt squared. This is a vector equation. So now what I'll do is that I will just I'll focus, first of all, mass cancels out, so you have a simpler equation, And so what I'll do is that I will write this, what I have here on the left side, in terms of r hat, theta hat, and you'll see that, that will simplify things a lot. That is why I started with describing the polar coordinates, because in polar coordinates, okay, this calculation, okay, solving for r becomes really easy, okay, and the reason is that the gravitational force is always, depends on the distance r and is directed toward the center. So, the polar coordinate actually works better than the Cartesian coordinates, okay? All right, so I'm going to simplify this expression, acceleration, in terms of, the polar coordinates, okay? Let's do that. So what I'm going to do is I'm going to erase everything except these relationships, okay? So, and let me just use a different color. So r, the radius vector, is r, the magnitude, times r hat, okay? Now, by the way, one of the things is r hat and theta hat, okay, they change the direction constantly, okay? Because they're following, it's it's a vector that's, that's pointing toward the particle, right? It's moving, so r hat is, the particle moves, so the r hat changes its orientation. And so does theta hat, because theta hat must always remain perpendicular to r hat, okay? All right, so this is the expression for r, okay, the radius vector. So if I take the derivative of r with respect to t, okay, I'll have to use the product rule. So I'll write dr dt r hat plus r dr hat dt, right? It's the standard product rule of calculus, right? So I'm going to call this as r dot r hat, okay? And this thing I'm going to write as dr hat d theta dt, okay? I use the chain rule here, okay? And why did I do that? Because, dr hat d theta is just theta hat, okay? And d theta dt is theta dot, okay? So I can write this as r dot r hat plus r, this is theta hat and this is theta dot, so r theta dot theta hat. All right? Okay, so this is the expression for the velocity. Okay, let me write this one down here. Okay, these are all the important formulae. Okay, so I just got dr dt is equal to r dot r hat plus r theta dot theta hat. Okay, now I want to find the acceleration, right? So what I need to do is d2r dt squared. Like I have to take the derivative of, of this whole thing. So let's write that down. So d dt of r dot r hat plus r theta dot theta hat. Okay. So now you kind of get the idea, right? I mean, how to, what we're trying to do. We will just go term by term. We'll take derivatives term by term. Like, d dt of this would be, we have to use the product rule to find the derivative of this, and then, product rule for that one too. And whenever we see dr hat dt, we have to use these expressions, okay? So, for example, let me just write it down here. So, in the first term, when we see dr hat dt, we will write this as dr hat d theta dt. So this is just, dr hat d theta is theta hat, and that is theta dot. Make sense? So that is really the plan, okay? So that is how we will take the derivative. So if you do that, if you go through the calculations, which I'm not going to show here, I'll just write down the final results because it's a straightforward calculation. If you have understood how to get this, you should have no problem, doing this one, okay? So the final result is d2r dt squared. This is the acceleration, and that is equal to r hat, r double dot, okay, minus r theta dot squared plus theta hat, r theta double dot plus 2r dot theta dot. Okay, so maybe I should just put a line here. Okay, makes sense? So, so this is the r hat component, this is the theta hat component. All right? Okay, so now what we're going to do, we're going to set this equal to, remember, minus gm over r squared r hat, on the right side. This is what you have on the left side of Newton's law, Newton's second law of motion. And on the right side, you have the expression for the gravitational force, right, which is given by this expression. Okay? Now notice something very interesting. So you have a theta hat term on the left side, but there is no theta hat term on the right side, right? So that means this thing is equal to 0. Okay? Okay, so let's actually write this down. Okay, so I'm just listing, down all the important formulae on the right side because I may have to refer to them again. Okay, so let me do that. So what we got is d2r dt squared is equal to r hat, okay, r double dot minus r theta dot squared plus theta hat r theta double dot plus 2 r dot theta dot. Okay. Also, I think you can actually try to prove these results. Okay, just if you want to practice. Okay, what we just discussed. Okay, this is a good place to sort of start and try to prove all of them. Okay, so this is equal to minus gm over r squared r hat. Okay, all right. So I'm going to erase what I did here now. Okay, so we concluded that this expression is equal to 0, right? So let's write that down. So you have r theta double dot plus 2 r dot theta dot equal to 0. All right, why it is 0? Because on the right side you don't have any theta hat term, right? So that means this expression has to be equal to 0. Okay, if you want both sides to be equal, then you have to have this equal to 0. Okay. Now, if you multiply both sides by r, a very an amazing thing actually happens. Okay, so let's actually multiply both sides by r. Okay, so on the left you have r times, on the right it's 0, right? 0 times r is 0. Okay, so let's distribute r to these two terms. So you get r squared theta double dot, and then you have plus 2 r dot theta dot equals 0. Okay, now notice that this is a total derivative. Okay, that means you can write this as d dt, okay, of r squared theta dot. You can write this as a time derivative of of an expression. Okay, this is called the total derivative term. Okay, and you can check it. Okay, so the first, if you apply the product rule, you'll get r squared theta double dot. That's the first term, and then this term. Okay, so that is 0. So that means, if d dt of something is equal to 0, that means that something is a constant, right? And I'll call that constant as L. Okay? All right, so that means theta dot is, okay, so that's another equation. Okay, so I'll just write that down here. So I have r squared theta dot equal to L. Okay, that's the other equation I got. Okay, so these two and then this one. I could have boxed them, but it will look messy. But okay. All right, so now this expression has a very interesting interpretation. Okay, it is related to Kepler's law. Okay, Kepler's law, one of those Kepler's laws, which says that in the rate of change of area that a planet sweeps, okay, as it moves, okay, is constant, right? So let me just explain. What that means and why that is related to this expression. Okay, so let's say that a planet moves like this in a trajectory. Okay, so and this is theta. Okay, it's moving like this. Okay, so let's say this is the small area. Okay, that it covers in a time dt. Okay, so the area in polar coordinate, this dA is half times r squared. Okay, times d theta. Okay, where do I get this formula from? You can actually show it very easily. If you consider this triangle, okay, and you drop a perpendicular, okay, like this, okay, and you use the formula half base times the height, okay, is the area of a triangle, then you can prove this. Okay, so for example, let me just do it here. Okay, so what is this? What is the height? It's r. If r is the radius vector, then this is r d theta. Okay, so what you're doing is half times r d theta, right? You see that? Half times, so this acts as a base, okay, and this is the height, okay, of this triangle, okay, and this is the area which is equal to that. Okay, now if you divide both sides by dt, okay, what you get is half r squared theta dot. Okay, but r square theta dot is a constant, right? So that means dA dt is also a constant, okay? So the rate of change of area that the planet or the object sweeps through, okay, is constant. Okay, that's one of the Kepler's laws, right? So anyway, and it follows, it follows directly from writing law of gravitation in polar coordinates. All right. So we haven't made use of the inverse square law yet. Okay. Okay. Another way to see, another way to sort of appreciate the physical significance of these is to look at angular momentum. Okay. So let me just explain what I mean by that. So when a planet moves, okay, when any object moves, okay, so the angular momentum is given by L is equal to R cross P, right? And P is m, m times the velocity, the mass times the velocity, which is m dr dt. M is a constant, so what you can do is that you can do the cross product. So you write m here and R cross dr dt, right? So this is dr dt, okay? So let's actually, let's try to do it here, okay? Just use a different color. Okay, I'm just working on this part now, all right? So I'm going to do it here, okay? So R, okay, I think it's probably too faint to see this color. So I'm going to use a different color. So R is what? R is R hat, right? That's the radius vector. And dr dt is that expression. Dr dt is r dot r hat plus r theta dot theta hat, right? So when you do r cross dr dt, okay, what do you get? R hat cross r hat gives a 0, right? But r hat cross theta hat, r hat is in the direction of the radius vector, right? And theta hat is perpendicular. So if you do r cross theta hat, so you get z hat, okay, as the cross product of two vectors. So you have z hat, and you multiply these two, you get r squared theta dot, okay? And you can do it carefully. I'm probably hurrying a little bit because this is really a side issue, okay, to my showing that the path, of a planetary of a planet is elliptical. But anyway, so if you do it slowly, you will see that this is what you get, okay? And this term shows up here, right? We just showed that this is constant. So that means this angular momentum is constant, okay, for a planetary, for a planet basically, okay, moving under a central force, okay, the angular momentum stays constant, which you can appreciate from the argument of torque, right? So what happens is that if you have a central force, a force directed toward the center, the torque, R cross F is equal to 0. So that means the angular momentum has to be conserved, okay? So this follows from really multiple arguments, okay? I mean this follows from, just from Newton's law, okay? And you can use other arguments, okay, to arrive at the same conclusion, all right? Okay? All right, so I'm going to erase all of these things. So these are my equations, okay? Right. Okay, so now is the final stage of the derivation, okay, of showing that the planets actually follow, an elliptical trajectory, okay? So what we're going to do is that I'm going to equate the r hat to r hat, okay? That's the next logical step, right? So there was no theta hat, so that's why I set this to 0. But now, the next step should be to equate the two r hat components, okay? So let's do that. So I'd have r, okay, I'm going to use the black color. So what I have is r double dot, okay, minus r theta dot squared is equal to minus gm over r squared. Now theta dot can be replaced by an expression involving r, actually, right? So theta dot squared would be L squared over r to the power 4. Okay, I simply replace theta dot by L over r squared, okay, from this equation, and you get this. So it would be r cubed, okay? Now this equation, okay, so this is a differential equation of r. You can solve it as a function of time, but it becomes easier to solve, okay, and it becomes easier to see that a planet, follows an elliptical orbit. If you make the following substitution, if you write r as 1 over rho, you introduce a variable rho in this manner, okay? how can that simplify this? It seems like it's going to complicate things, right? But actually not. I mean, as I'm going to show you, okay? So what I'm going to do is that I'm going to take the derivative of r, okay, with respect to time. This is with respect to time, These dots are the time derivatives, right? So let's do r dot first, okay? So r dot is going to be what? 1 minus, I have to use the chain rule, right? So dd rho of this, right? And then you have d rho dt, which you can write as d rho d theta times d theta dt. Okay? So now this is this is this, and you have d rho d theta, and this is theta dot, right? But theta dot is L over r squared, right? And what that means is L times rho squared, right? L over r squared is L times rho squared, because rho is 1 over r from this, from this equation, okay? So rho squares cancels out, so you have minus L d rho d theta, okay? So one more derivative, right? I need to do r double dot. So minus L is there as it is, so I'll write this as d2 d theta squared. Once again, I'm using the chain rule, right? I'm first taking the derivative with respect to theta, and then d theta dt, which is theta dot, and then theta dot is once again, L over r squared, and that means L times rho squared. Okay? So, right, it's just the same thing, you can use this repeatedly, okay, and you'll get, and this expression, and you'll get this, okay? So, L times, so you have minus L squared, right, and then rho squared, and then d2 d theta squared, okay? And this doesn't look, still doesn't look quite impressive, right, in terms of simplifying this expression, but it will be, okay? So, I think you'll see it right now. So r double dot is that, so let's write this down, minus L squared rho squared d2 rho d theta squared, okay, and then minus L squared okay, this thing is 1 over r cubed, right, so it should be rho cubed, and on the right side, okay, I have to be, I'm sorry if it causes confusion. So all I'm doing is that I'm just writing, I'm focusing on this equation, okay? And I'm going to make use of this, okay, and this definition, all right? Okay? So r double dot is what I got there, okay? This is the first term. And then you have minus L squared rho cubed, right? 1 over r cubed is just rho cubed. And then on the right side, I'll write minus gm rho squared. Okay? And then divide both sides by L squared rho squared, because you'll see a lot their rho squared will cancel out, right? So if you do that, you're going to get this expression d2 rho d theta squared, okay, plus rho is equal to gm over L squared. Okay, just that. I mean, right? If you can see that you can cancel out rho squared, and this one will give you just one rho term from here, and you're also dividing both sides by L squared, so this is your equation. Okay. All right. So let's erase everything, except for keeping this equation, okay? Because this is what we're trying to solve, and this is way simpler than solving this thing, okay? Why? So before I erase it, let me just tell you why exactly. Because this is the equation of a harmonic oscillator, really, right? I mean, you know the solution of this equation, okay? And here you have a constant term, so you'll have you need to consider homogeneous solutions and special solutions, right? And then add them together to get the general solution, okay? So let's actually do that, okay? So, but it's really easy to writing down the solution, okay? So things did simplify, okay? That's my point. So my equation is d2 rho d theta squared plus rho is gm over L squared. Okay. Now, how do you solve this? So for these, for these types of differential equations, you first find the solution, the homogeneous solution, which means you set 0 on the right side and then solve for rho. Okay. You write equal to 0. So rho is given by a cosine theta minus theta 0. Okay. It's of this form. You can actually write it as a cosine theta plus b sine theta, which is the same as, which is equivalent to this statement, okay? Right, you can go back and forth between these two forms, okay? So rho is given by this equation, and this is rho homogeneous, and then you have rho special, okay? And special solution means you look for that one solution, okay, which will satisfy this equation, with a source term, as they say, on the right side, okay? So you have to guess, okay, what is the special solution? Well, just rho equal to constant. Let's say rho is just a constant term, and then the first term vanishes, and then that constant term is what you have on the right side, right? So rho special is going to be gm over L squared, right? So rho, the net solution, is just the sum of these two. So you can write this as gm over L squared plus a cosine theta minus theta 0, okay? But what is rho? Rho is 1 over r. Remember, so r, the radius vector, is 1 over this whole thing. Okay? And this is the polar equation of an ellipse, okay? Where the center is, from which r is measured, okay, is one of the two foci. Okay, it's I don't know if it looks familiar to you, but let me show you. You can actually derive it, okay, from probably a slightly better known equation of an ellipse, okay, in the Cartesian coordinates. Okay, so let me just show you how to get this from better known equation of an ellipse. Okay, so let me do that. I'll just outline the proof. It's it's a matter of algebra to do the rest. So I'll keep this last expression, okay, because this is the equation of an ellipse, as I said. So what I'll do is that, so I'll talk a little bit about an ellipse, okay, and the equation that describes an ellipse, all right? So an ellipse it looks like this, okay, and these are the two foci, okay. So what is the equation of an ellipse? It's x squared. So let's say this is the x-axis, this is the y-axis. So you can write x squared over a squared plus y squared over b squared equal to 1. Right? So this is the equation of an ellipse. Alright? So now, let's say you transform you shift the y coordinate to the left. Okay? You bring it here so that your origin, you leave x as it is, but you move the y-axis, to your left. Alright? So this is your new origin. Okay? Why did I do that? Because, I want to write r, the radius vector, okay, in terms of, rectangular coordinates. So if this is r and this is theta, then in your next, okay, so first let me just write down the relationship between the two coordinates. So I call the new coordinates, okay, as the prime coordinate. So your x prime is equal to x plus ae, okay. So where did I get that? What is AE? So these are the coordinates, the coordinates of the foci are AE comma 0, and this one is negative AE comma 0, okay? What is E? E is called the eccentricity, okay? Which is given by, so if this is the equation of the ellipse, then E is square root of 1, okay? So this is the expression for the eccentricity, okay, of an ellipse. And the two foci are at these coordinates. So what I did is, I moved I shifted the y-axis to the location of one of the foci, okay? So then x prime, that's the x in the new coordinate system is, given by x plus ae. X is the x in the old coordinate system, and your y prime doesn't change, so y prime equal to y. All right? So what you'll do is that you'll write this equation in terms of your your new coordinate systems, right? X prime and y prime. So if you do that, then you need to replace x by x prime minus ae. You have to move this over to the left, right? Because you have x here. So you'll have x prime minus ae squared over a squared plus y prime squared over b squared equal to 1. All right? Next, what you'll do is that you will replace in this equation, you will write x prime is equal to r cosine theta and y prime equal to r sine theta. Okay, you just replace x prime by r cosine, because r is this, the polar coordinate, the radius vector, the magnitude of the radius vector, right? So you replace x prime by r cosine theta and y prime by r sine theta, okay? So now we have an equation which involves r and theta, all right? Okay, and if you simplify this, you'll get an equation like this, okay? It doesn't look obvious, it's like you have e and so on, but you know, I mean, you just have to do the algebra, okay? Which might be a little bit messy, but at the end, you will get, you know, if you replace x prime by that and y prime by this, then what you'll get, I'm going to write it here, you'll get an expression which is r is equal to 1 divided by a over b squared plus minus e times a over b squared cosine theta. Okay, which is very much like this, okay? I mean, this theta 0, you know, there is no theta 0 here, but that is because, you know, I just chose theta 0, you know, to equal to 0, okay? So that's just a matter of, you know, choosing your x-axis, okay? But you can see that this looks very much like what we got by solving Newton's law, okay? Using the, you know, gravitational force, all right? So that means this is actually the equation of an ellipse in polar coordinate system. So this is how r changes with theta, okay? So that means the planet describes, okay, an elliptical orbit with the sun at one of its foci, all right? So, and once you have found r as a function of theta, you can find, you know, how they change with time, you know, from this equation. And I think, yeah, I mean, literally from, I think from this, you can use this equation, okay, to find that, okay? But, you know, this equation shows clearly that the planet follows, you know, an elliptical orbit, okay? So I hope you enjoyed the video, and thanks for watching.